Okay. Let's see, why do I have all of these screens? It does not make sense. I think this is the one. Cool. All right, can everybody see this?
Yep, I can.
Cool. All right, so let's see. Unfortunately, this week I did not get as far as I wanted to with all of these, going with the fancy slides. I tried to, I guess I bit off a little bit more than I can chew. Went a little deep with some of this, so, but we'll see. Hopefully this is good, and worst case I can jump over and finish up with the other slides. There's a few architectures I wanted to touch on that I thought were nifty that were not included in the original video. So, but yeah.
Yeah,
so,
I think my 2 cents, Jonathan, before we get on that subject is, yeah, you could probably have next week as well. I also wanted to kind of solicit people to take up either going to the homework and or collab of this particular section, because I still don't have volunteers, and for personal reasons, I won't be able to do as much this week or the next week. So something for people to watch out, or else, we may have to just make do with somebody taking us through the code, but nobody has stepped up yet. So I'd like to solicit volunteers to do that. So you could anyway have some time next week as well.
okay, that sounds good. And actually, so I don't know that I would go too much more in depth. I kind of punched a little bit higher than I probably should have. Mainly, I'm like you. I'm running a little bit low on time, so I can definitely finish it out next week. I think that would be good. I don't think it'll end up being like a full hour and a half or 2 hours or something.
That's fine. That's fine. I mean,
yeah, I'm actually I've got to do a proposal defense fairly shortly, so that's a drawing on my resources. In my, I don't think my professors will be too happy that I'm spending my time doing something else. But
absolutely.
Yeah. So cool. But yeah. All right, let's jump on this. So quick recap on this, normalizing flows. So what are they? Well, it's a sequence of invertible and differentiable mappings. So that is the flow. So that sequence of mappings, that's the flow, that transforms a known tractable distribution where both the evaluation and sampling are easy into another potentially complex but still valid probability density, hence the normalizing. So the flow comes from having this sequence of invertible and differentiable mappings. And then the normalizing part is ensuring that you end up with a normalized density at the end. So you're starting with something that's like a normalized density, and you're squishing it and squeezing and transforming it so it looks like something else, but you're making sure, once again, that all that probability mass under there is, conserved, right? So the relation between these distributions is expressed by the change of variables formula, and that is how we ensure that that probability mass is conserved during the transformation. I actually do like the focus on, probability. Everyone talks about like, oh, it's a volume correcting term, and it's a volume correcting term. And it's true that the Jacobian is like a volume correcting term there. But as we see with some of these architectures later, some of these transformations are volume preserving and others are non-volume preserving. But the key point is what you end up with is still a legitimate probability density. I think that's like the key takeaway, right? So, that confused me a little bit too, because you read this, oh, this is like, ensuring that this is altering volume, and then we came across some of these like, real NVP, non-volume preserving. So like, okay, well, why would we have volume preserving versus non-volume preserving? And we'll touch on that later. But point being, we just want to make sure that what we end up with is a legitimate probability density. So also these flows can be composed together, hence that sequence of invertible differentiable mappings. So you can just take a whole bunch of these flows, stick them together, and you end up with the overall flow. And then if you want to invert that, then it turns out that the composition, the inverse of the composition is the composition of the inverses. So so just some nice properties with these. And so it's kind of like, reminiscent of other things we do in deep learning, where we take, a little transformation that's relatively simple, and we, stack it together, we ensemble them together, and we build up, and we can make something, much more complex. So yeah, so each additional stage in this composition is just going to add an additional volume correcting Jacobian term, like so. So yeah, so just every time you do one of these transformations, it's going to essentially push up, push down. But yeah. All right, and the great thing about this is these normalizing flows can be trained with our usual MLE and stochastic gradient descent, with these additional contributions from the Jacobians, of course. And so we should be familiar with this by now. So just like maximizing the log probability, and then you have this little adjustment to that log probability. And so some of the requirements, right, to train and use these flow models. First of all, we have to make sure that our X and Z's, and I will go ahead and apologize ahead of time. Because I drew on so many sources here, sometimes I'm using, Z, sometimes I'm using Y. So, if anybody gets confused at any point, please just flag me, and I'll do my best to like iron that out. But yeah, so first of all, we want our, basically our data, the X for like our data, and then the Z is essentially our base distribution. So X and Z must have the same dimension. So they must both be in Rn. We also need to have differentiability, right? It needs to be indifferentiable. We need to be able to invert that transformation. This is something that's not always the case. I mean, I guess we kind of think about like differentiability and invertibility kind of closely tied together a lot of times, but a lot of neural networks don't do this. I mean, you can even think about, I'm taking this off the top of my head, but if you have like a max pooling operation, or there's a lot of things we use when we're going from an input to getting an output that are not necessarily going to be invertible. You have to be very careful about that. So that is one of the tricky things about these flow models. That differentiability, that's kind of taken for granted, but invertibility, that is tricky. And we also have to have this tractable Jacobian determinant, right? Oh, did not mean to jump that fast. So I'm going to pause here real fast. So anybody have any questions about this stuff so far? This is pretty much what we covered last week. So what is a flow? What is a normalizing flow? Properties of the compositions. How do we train them? And then, what are the end goal? What are some of the requirements we need for these? All right, everyone good?
Just one small thing was that all of these the X and Z's, they all always have to be the same dimension, right? You can never change, even if you have a whole sequence of them.
Right. For any one of your X inputs, variables, dimensions, what have you, you need to have a corresponding one in your Z space. Yep. So
does the Rn have any relationship to a neural network, or can it only have like n variables, or is just something abstract? Maybe you'll follow.
So what I'm saying, like the R, so the R part, that's just gonna be the continuous, right? Like as opposed to some of what we were doing before with discrete. Well, I guess we weren't working with discrete predictors even, but discrete targets is what we were working with. But either way, basically both of these are going to be continuous n-dimensional spaces.
But n means, like, for example, the image, number of pixels in the image, right?
Right. So give a, yeah.
So, but in CNN, what we do is we, make it smaller or increase the number of channels, like change the shape, right? So will that cause problems? Because then you're starting from n, and then you maybe become some other number,
Right. You're hitting on an important. Yeah. You have to keep track of all this.
Okay.
We don't have the luxury of being able to just like pool them, squish them down, throw away ones we don't want. Yeah, we have to be very careful if we are doing any kind of dimension reduction. We've got to be very careful that we keep track of where everything's going. And that goes back to like the invertibility thing, right? You know, you can go from, you could map, you know, something three-dimensional to a single point. I mean, I guess let me think here for a second before I speak out of. So I don't know for sure. Whenever you go from a higher dimensional space to a lower dimensional space, I'm not sure. Is it necessarily going to be non-invertible?
Yeah, it has to be.
Yeah, you're losing information.
Yeah, yeah. So there you go, right? So anytime you're dropping those dimensions, then you're going to lose your ability.
So also the other thing is if you go from Rn to maybe say 2n, but somewhere down the road you have to go back to n, so then you'll lose information. I think that's why all of these sequences of spaces have to be all Rn. It's the same size as your input.
Right, and that's not always the case for, you know, these generative models, right? Like with the variational autoencoders, that latent space is generally speaking going to be a much lower dimensional one, right?
Yeah, and yeah, I do remember him talking about it somewhere in the lecture about the latent space. So then if you have a million large latent space, then it's anyway, yeah.
Yeah, in this case, what would happen is when you reconstruct your, reconstruct your input back from the compressed thing, right? You are only, your autoencoder is trained to, reconstruct only in a certain domain. It is not trained to reconstruct, from the lower dimension to the higher dimension in all cases, right? So that's the, the kink there.
Yep. Yeah. Cool. So let's see. So yeah, so this introduces some of the trickiness, right? And you'll remember back at the very, very beginning, I showed a, let me see, I probably have to jump out of this. I don't know if I can just jump to one of my previous slides. Let me see here. Oh, yay, there we go. Cool. Yeah, if you guys remember this one from before, it's like you look at flow and it's like, man, the flow model looks like it has everything we're looking for, right? So we've got, exact sampling, exact inference. We've got a meaningful latent space. We can do stuff with continuous X's. Like, just seems like this has all the nice properties we want. So like, what's the tricky part? And the tricky part is, you've got to be very careful about how you actually design that architecture, right? There's constraints here that we have to obey that some of these others don't have to obey. Yeah, so getting to it, right? Yeah, so what's the catch? Right, flow models seem great. Well, the question is like, how are we actually going to design this flow, right? We want to design one that's going to be highly expressive. We want it to be easy to invert. We want it to be efficient to compute the Jacobian determinant. And let's note real fast that there tends to be a trade-off between the first property, this expressiveness, and the second and third properties, which would be the easy and efficient computation. And I like this little chart. And by the way, at risk of making my next presentation next week look like garbage, I'm going to point you guys to a fantastic YouTube lecture, which is where I pulled this from and a couple other things. It's very good. You actually see the little URL down there at the bottom. Yeah, so you can see here that depending on how we choose the structure of a particular, or how we structure a given matrix, we can determine how expensive is it going to be to compute the inverse or to compute the determinant, right? So this gets to efficient, easy to invert, and efficient to compute the Jacobian determinant. You can see that in some cases, one is more expensive than the others, right? In the case where we don't have like any restriction, and we're going to revisit this in 1 second, but and we probably will pop back and forth to this table. But you can see this is where we get into having to be clever about how we design things. So yeah, for example, like a full matrix, right? With no restrictions on there whatsoever, generally, it's going to be, big O D cubed to calculate the inverse and the determinant. And that's obviously super expensive versus a diagonal matrix, like, for element-wise flows, it's just, big OD. That's not going to be bad at all. It's just going to be linear. So, but of course, once again, there's trade-offs, right? A purely diagonal matrix is not going to be very expressive, right? Especially as compared to that full matrix. So we're gonna touch on this more in a second. But point being, designing a flow that is highly expressive, easy to invert, and for which it's efficient to compute the Jacobian determinant, this is not easy, and we have to balance these trade-offs. So the way I'm approaching it this week is, instead of jumping straight off into the architectures, which is kind of what happened in the lecture, and it's interesting and all. I mean, I get why. It's like, it depends on what your approach is, but I kind of want to know, like, why? Why did someone come up with this architecture? What's the point? And so that's why I kind of wanted to go through the types of flows, these different, broad categories, before jumping off into the architectures, because this sheds a little bit of light on, why these different choices have been made. What's the method to the madness? And so we're closely going to follow this Kobizev 2020 paper. I think I posted that in the resources last week. And this is a chart taken from there. And so we see a little bit of a summary of what some of these are, and then some of the problems they have. And so we're going to address those. I don't jump off into planar and radial flows. Maybe if I have this next week, I might bring those in. Those are actually closely tied in with these residual flows, which is something else that wasn't covered in the online lecture. So the way I kind of group these together is we sort of have element-wise flows. Then we can think of just general class of, so when I say element-wise, I'm talking about just like generally non-linear element-wise flows. So let's just assume that all of our dimensions are independent, like make a really strong independence assumption, but then we can, along each dimension, do really complicated nonlinear, mappings. Then we've got linear flows. Then we have autoregressive and coupling flows. This is something that was not immediately obvious to me from the lecture, was that there's a very strong relationship between autoregressive and coupling flows. Those two things are very closely tied. In fact, coupling flows are a kind of autoregressive flow. And then the residual flows are closely tied with these planar and radial flows. And then finally, we have these continuous flows, which are like the fjord architecture. And I know Ryan posted some stuff on that last week, and I'm actually looking forward to poking through that. I did not get quite to continuous flows yet. But yeah, so this is not going to be a comprehensive examination. There's plenty of other approaches, but hopefully this will be enlightening. So let's start off with element-wise flows. What is an element-wise flow? Well, the idea for this is, can we apply an independent nonlinear transformation to each element, like so? So instead of taking into account the relationships between x1, x2, x3, blah blah blah, then we just take this one function, and you could have a separate function for each one, or it could be kind of a parameter sharing thing. You'd be like, okay, well, I'm just going to apply the same function to each element, right? So there's lots of choices there. So you could, so that could be the same mapping for each one, or you could have a separate mapping. But why would you do this? Well, the primary reason you would do this is that the Jacobian ends up being diagonal, right? So the determinant then is just going to be the product of the diagonal elements. So that's really nice. And a lot of times you're going to see, we're going to be talking about invertibility, like what's the cost of inversion, what's the cost of calculating this Jacobian determinant. And honestly, at the end of the day, calculating the Jacobian determinant is probably going to be your bigger bottleneck, right? Because every single training step you do, if you're using like stochastic gradient descent, you're going to have to do this. So that's probably going to be a bigger factor when you're thinking about like how I'm going to design this. Like, okay, maybe it's really not straightforward to do the inversion. But you know, once I get that figured out, or once I compute it once, maybe I can reuse it for a trained model. But for these models, like during training, we've got to continually compute this thing. So this is critical. Like being able to compute that determinant of the Jacobian very quickly and very cheaply is extremely important. So that's pretty much why you would use the Elementwise flows. And then it's fairly flexible as long as, once again, as long as what you're dealing with, this assumption that the elements are independent of one another. If that is a good assumption, if that holds, then you know this is excellent. This works fairly well. It's cheap. It's very flexible because you can choose whatever you want for that f theta, as long as it's easy to invert. So, so depending on the nature of your problem, it could be very expressive. But the second that independence assumption is violated, this just does you no good. Okay. So everyone good on element-wise flows?
Yep.
Cool. Yeah. So their big problem, the big bottleneck, limited expressiveness. There's no ability to capture any correlation or nonlinear analogs between the variables. So linear flows. Well, let's think about using an affine transformation. So why would you do this? Well, this is actually able to capture correlations between the variables, unlike the element-wise flows. Conceptually, this is very simple and just requires that A be invertible. And essentially what this does is just going to shift and rescale. So whatever our input is, we can shift it and we can scale it. So it looks something like this, right? So we sample from our distribution, like maybe it's multivariate normal, and then we shift and scale. Right? The Jacobian is just going to be A inverse. You can see that pretty easily. So dz dx. So you can think about that f theta x up top. Here's your z equals all this. So dz dx. This falls away. You just end up with A inverse. So that is just your Jacobian. This is mainly just going to be a conceptual building block. It is very limited in its expressiveness, once again, since a composition of linear transformations is just a linear transformation. So, basically, if you start with something in the exponential family for your z, you're going to stay in the exponential family. And so this is going to be expensive to invert. That's another major problem. So again, this is like a lens. We can talk about the nonlinear stuff later and this whole thing. Oh, well, we're limited to linear transformations, but this is really going to be where we can tease out some very important concepts. So if we don't have any restrictions on A whatsoever, then it's going to be very expensive to invert it, and it's going to be very expensive to calculate the determinant. It's going to be big O D cubed. So the question then is, can we add any restrictions to improve this? Right? This is just extremely expensive. Just disregarding the whole limited expressiveness, let's assume for the time being, while we're talking about linear flows, let's assume for the time being that we are dealing with, we are in a problem domain where a linear flow is adequate. Right? So let's just assume we've got enough expressiveness. Now, like, how do we actually do this in a way that is efficient? Well, the first thing we might think about doing is just going element-wise, right? So back to those element-wise flows a minute ago, we were talking about nonlinear element-wise flows. Well, we could just do an element-wise linear flow. This is like the simplest and easiest possible thing to do. Right? So, A is just this diagonal, like it's essentially a coefficient vector, right? So it's conceptually very easy. It's computationally very easy. The inverse and the determinant are extremely cheap. You just calculate those in linear in the number of dimensions. The Jacobian is going to be diagonal. The determinant is just the product of those diagonal elements. So this is pretty much the simplest, cheapest, and easiest thing you can do. But it's also probably the most limited. So it can still be useful, as Kobazev points out, for representing normalization transformations, which you see in neural networks do. But really, it's just too limited to be useful. But it's a starting point, right? So what else could we do? Well, what if we let that matrix be triangular? Where we do a triangular transformation, right? So we get something that looks like this. So we've got, coefficients along the diagonal and, below the diagonal, but, the upper triangular is just all zeros. So why would we do this? Well, it's going to be more expensive than more expressive than an element-wise transformation. But the determinant is still just going to be the product of the diagonal entries, right? So we maintain our computational efficiency in terms of like calculating that determinant. It's still just going to be, big OD. And the inverse is actually a little bit cheaper as well. So remember that full matrix, the unrestricted, if we wanted to calculate the inverse, it was d cubed. And if we wanted to calculate the determinant, it was d cubed. And so here we've saved a little bit on the inverse, and then we've really saved on the part that we actually care about, which is the determinant. And in fact, our determinant is no more expensive to compute here than it was for the element-wise, but we've got significantly more expressiveness. So, this is pretty good, right? So what are the problems? Anyone have an idea about what kind of problems we could run into here?
I'm guessing accuracy loss, but not sure how. I mean, well, obviously there is less, the upper thing is gone.
Yes, there is a limited expressiveness. So, but in particular, the expressiveness is contingent upon the ordering of our dimensions, right? So if you look up there at the top and you think you've got, if A is basically, dz, in this case, if we think about dz dx, right? So put z on one, x on the other, you can see that one of, let's say, let me see for a second, just I've got this set up. So A would here would be, so A inverse was dz dx. So here you could think about having like your x essentially on the vertical axis. Think about having your z right here. So effectively what you're saying is x1 is only going to be related to z1, x2 is going to be related to z1 and z2, x3 is going to be related to z1, z2, z3. So you see, you basically, the expressiveness you have for any particular dimension is going to be contingent upon where it is in that ordering. And that should be reminiscent of something that we've looked at recently. Right? Looks a little bit like autoregressive, right?
Yeah.
Yep. And there's a very good reason. So we will revisit that in a second. But yeah, so the last dimension that you have is going to be the one that actually has the most expressiveness. But and obviously it's still linear. But one question is, how can we get around this? Is there something we could do? Well, what about permutations, right? So if we use permutations, then maybe if we have this whole sequence of triangular transformations, we can use permutation matrices to shuffle things around a little bit and ensure that we get conditioning, adequate conditioning along many different dimensions, right? So that permutation matrix allows us to reorder them with very little added effort. It improves the expressiveness of the triangular transformations when we use it alongside it. And the inverse of a permutation matrix is its transpose. So that's pretty easy. That's super simple to calculate. And then the determinant is just 1, right? Like it's literally there's nothing you have to do. You know what the determinant is. So the most expensive part of our training process, this adds essentially no overhead. So yeah, and there is a more general approach using orthogonal matrices that we don't delve into here. But the takeaway is if you use a sequence of permutation and then triangular transformations, this may not be as expressive as the unrestricted, but it's a heck of a lot better. And so I want to drive this one home because now we are building up some building blocks that will show up later.
So each iteration, you're looking at a different set of autoregressive relationships, right?
Right. So you can think if we applied one of these permutations and just shuffled the dimensions, and then we did a triangular transformation, then that dimension at the top is going to have, it's only going to be conditioned on one thing. But then maybe we shuffle, or maybe we reverse the ordering on the next step, and then we ensure that, so basically we can ensure that everybody gets a fair shake. So those permutations allow us to shuffle the dimensions and ensure that everybody gets to condition on everybody else.
Right. It's a bit, it's basically sampling, right? Yeah.
Sorry, one more time.
It's like sampling, so essentially, if you think of an autoregressive thing, you're basically permuting the time axis, right? So each time you're looking at a different sequence of things, and you're getting, so essentially you're sampling the time axis in different ways, I think. I mean, it's
well, so it's like the MADE architecture, right?
Yes.
Remember when they talked about MADE, where you had like, well, how many masks should you use? It's like, well, we have one very specific ordering, then we end up with something that's pretty inflexible. But by using a whole bunch of masks, and actually, I guess what was it, like 8 or 10, you got a lot more expressiveness.
Right.
Yep, same idea, exactly the same. And in fact, those autoregressive masks are triangular. They are triangular transformations.
Yeah.
Yep. So bingo. So finally, one other interesting approach was to say, what if we don't even need to restrict the form of A at all? Right? What if instead we just factorize it? Right. So can't remember who it was that proposed this one, but this using an LU factorization, right? So L is the lower triangular with the ones on the diagonal. U is upper triangular with non-zero diagonal entries, and then P is a permutation matrix. So, so the idea is, if we can, instead of learning A, right? Instead of learning that, what if instead we learn these factorized matrices instead, right? Now, why would you do this? What benefit do we gain from the factorization? Well, the first benefit is that the determinant is just going to be the product of the diagonal entries in U. Right? So that's super nifty. Determinant of P is 1, determinant of L is 1, and then the determinant of U is the only one that's going to be non-trivial. Right? So that's just OD. So this is super cool, right? Because we started with Elementwise, where computing the determinant was going to be, linear, big OD, right? And now we've gotten all the way to this point where we're almost as expressive. And I say almost, you might be sitting here going, well, we factorized it, and PLU gives us A, how is this any less expressive? I'll get there in a second. But for the time being, just notice that it's no more expensive for us to compute the Jacobian determinant here than it was for an element-wise flow. That's pretty cool. But it is a little bit more expensive to compute the inverse, but no more expensive than it would be for a triangular matrix. So extremely expressive. But what is the problem? The problem, it turns out, is that permutation matrix. And this actually gets back to that previous one too. I didn't touch on this on the previous slide, but the issue with these permutation matrices is they're discrete and hard to optimize. So usually you just fix it, like you just choose those masks ahead of time, and in the same way you would choose your permutations ahead of time, or just usually just randomly initialize it. But the problem is, the second you're no longer jointly optimizing P with L and U, well, you've handicapped yourself, right? It's made it less flexible. So it's still extremely expressive, but you've handicapped it a little bit. So there is a proposal. I didn't look into this one deeply, but there is a proposal of using QR decomposition and something called householder transforms. I have no idea what those are, honestly. I would have to go poke around. But using this QR decomposition has apparently been proposed as an alternative that gets around that issue of having to fix the permutation matrix. And so that was a little bit tricky. Did everyone follow that one? It definitely tripped me up when I was going through this stuff.
It becomes a bit like simulation kind of approach, right? Where you basically say, okay, I'm sampling P, or I'm basically randomly assigning P, and therefore it must, I have covered enough of the sample space to be expressive enough. And so if I pass enough things, enough data through it, I will kind of get a nice coverage of the data that I'm,
yeah. So if you, it's kind of like the P almost becomes an architectural choice.
Yes.
Right? Yeah. So hopefully, apparently, the QR gets around that a little bit. But these are all the big building blocks, right? So Elementwise, you use Elementwise, triangular. What were all the ones I went through? My animations make it difficult to go through. Yeah. So we've got
it's like a lot of variants of linear algebra to factorize the matrices and calculate determinants and keep them simple.
Yeah. So just by putting some constraints, if we can ensure that our matrices are going to work out in some particular manner, that we basically we want to be able to exploit that structure. If we just let it be whatever it wants to be, then we've not put any constraints on it, but at the same time we don't really have much we can leverage. But yeah, so by ensuring that it's either diagonal or triangular, or we learn the factorizations, or employ these permutations, like the second we started doing that, we have some information we can leverage in the process of trying to actually determine these inverses, determinants, and speed up the training process. So
I have a quick question. Sorry. Yeah. It's probably if someone knows linear algebra. So in the previous slide, the LU decomposition, the QR, or also the SVD, right? They're all decompositions of any matrix. And so, do we still need the permutation matrix? Because I think the permutation is just to randomize the dependency, right? So. Slide went away.
Yep, all good. I was gonna say I have something pulled up for this.
Okay.
That was something I wondered about myself.
Okay. Yeah. So I was wondering, maybe you don't need to have the permutation matrix at all. But yeah. Okay.
Sorry, that bar at the top is making it difficult for me to. There we go.
It's been a.
So yeah, so apparently, and so it's been a while since I looked at like LU factor, like any of these factorizations, like LU, QR, like it's been years. So just like I had to go back to Wikipedia and poke around a little bit. But apparently, without a proper ordering or permutations in the matrix, the factorization may fail to materialize. Basically, to do this properly, I guess you have to ensure that you have the proper ordering, right? So it comes up down here. What is this? And anybody else who knows this better than me, please step in and go for it. But yeah, so it turns out a proper permutation in rows or columns is sufficient for LU factorization. Yeah, so there you go. LU factorization with partial pivoting refers to LU factorization with row permutations only. So yeah. So I guess the takeaway here is basically if you're you have to have the ordering has to be correct, I guess. Generally speaking, there has to be some specific ordering to it. But just I do not know this deeply. I don't remember off the top of my head. But yeah, so that P right there, right? Assuming that we have already permuted A appropriately, then all we have to do is learn L and U.
So it says it's for numerical stability, or the permutation, because you don't have to permute, right? Maybe it's for numerical stability.
Yeah, I'm honestly, I'm not sure. Like saying something about it being a procedural, I don't know if it's numerical stability or if it really is something about, because yeah, I'm rolling this around in my head as well. Like if we're trying to jointly optimize L and U given a particular P, well, I mean, even without that P, right? Yeah, I would just like, maybe
I
it's
think
this,
it's more
right? Maybe
than just numerical stability, as you're pointing out, because again, it's been years since I looked at it. There's a particular book which gets into these things with practical application. I'll post a link to it. But, as it says, I think the problem, if I recall, is the fact that if you don't order it correctly, then you run into this issue of the first value being 0, and therefore the procedure failing. But the procedure fails not because it will always fail, but if you reorder the rows, then the procedure will work. So that's why the P becomes important, and it's not just the stability, but it's also like you can't get a solution if your order is incorrect.
Okay.
Using this method.
Okay.
Yeah, and on that note, like, so yeah, I guess you'd think about that would be like shuffling these. You could imagine that if you shuffled one of these, right, that you got this like unique factorization. Now shuffle some of it, and it's like, well, one of them is no longer lower triangular, the other is no longer upper triangular, and maybe it's just that there's only one way that will ensure that you end up with a lower triangular and an upper triangular. But on the other side, though, I'm imagining if you're actually learning L and U directly instead of learning A, maybe I misunderstand what they're doing, actually. Maybe I thought my understanding is what they were doing was they were optimizing for L and U and not, A as a whole, but I'm wondering if maybe they are optimizing for A as a whole and then decomposing. I'm not sure, but it seems strange that that permutation would play such an important role. Like if, let's just say that I replaced L and U replaced A with a set of learnable weights L that were always going to be lower triangular instead of learnable weights U that were always going to be upper triangular, then I would think that it would kind of implicitly learn the permutation of A, because you never actually have to learn A. I don't know if that's what you're getting at, Mo-chan.
Yeah, that's yeah. I was just thinking the P was only for numerical stability, but yeah, if it's necessary, then yeah, that's yeah. I don't know if they're all three matrices are being learned independently, and the decomposition doesn't happen through the process, because I believe the decomposition is O(n) cubed, right, or O(n) squared. Yeah. So that wouldn't help if you learned A and decomposed it, or.
Right. So I would think you would just learn L and U with constraints on the parameters, in which case, why would you even need, because you could just go ahead and assume that replace PA with a new matrix A star, and then you have L star U star, and you're learning L star. It doesn't matter. Right. So I don't know. Maybe this is something in the training process, and I'm actually curious now. It seems like that would be an obvious approach. Why would you not just learn L and U, and then the permutation just, it doesn't really matter. But I don't know. These are some smart guys, so I'm probably missing something.
Yep. I think QR is not upper and lower triangular, right? QR, and SVD is diagonal, and D is diagonal. S. Yeah. So maybe this is nice because they're both diagonal, the L and U, but in QR and SVD, the calculating determinant probably isn't as easy. So that's maybe I don't remember what the structure of the matrices are.
Yeah, and this is very interesting, and it's I would be curious to poke around this a little bit more. But yeah, I know, for example, what was it with RNNs, something I looked at a while ago. I think it's called gated orthogonal recurrent units. I don't know if anybody's heard of those. But the idea being, it's kind of like this whole, another one is like unitary RNNs is another one. But the way you get around the gradient, gradient explosion or vanishing gradient problem is essentially learning these transformations that ensure the determinant is always one, right? And so I remember some approaches that were similar to this that involved like these clever factorizations or learning matrices with clever constraints on them to overcome that problem. And then you could essentially, actually, it was funny, I think the unitary RNNs, the issue that they had was they had perfect memory, right? And the problem is the ability to forget for recurrent neural net was actually very critical. If you remember everything, then it's hard to figure out what matters, basically. So this is something that crops up a lot. I think it's something I always say. It's like, I really wish I'd learned linear algebra like really, really well. Like I see it everywhere. But yeah, so.
Yeah, all I can add. Oops.
Oh, go for it.
Just say I was going to say I also learned that I need to learn more linear algebra, and I learned that this stuff is often called matrix analysis, not linear algebra.
Interesting.
And all I can add to our argument here is that as soon as you step away from complex numbers, the factorizations are harder. There's a sure decomposition that'll just, with complex numbers, you can go to upper triangular and be done with it. There's nothing else. So we're just kind of stuck in real number land, which is where the computers work.
Oh, maybe there would be something to the complex valued approach.
Yeah, probably. It's just that it typically takes twice as much memory. So you would have to have a really good reason, which could happen here for sure, since we're looking at determinants. But yeah, that's
I get at the end of the day, it's like, what's the trade-off, right? You've got spatial resources, temporal resources. Like it's like, which combination of these is going to be, where's your, what's the Pareto frontier for these things, right? It may actually be the case that, taking up more of those memory resources at the benefit of decreasing the amount of time it takes could be super useful.
I like to think so. I just know that just looking for libraries that want to work in complex numbers is typically pretty hard. But, we're just looking at models for now. So yeah, I like it.
Cool. All righty, we hop back to the.
Another small thing that I just occurred to me because sure decomposition. I think you mentioned householder transforms, right? And so I think one of the technique is to householders are rotation matrices, right? If I remember correctly, you can rotate. So there's a I don't know if there's a certain decomposition where you can rotate it around so that one of the matrices becomes low triangular. I think that's the point of the householders is you rotate your space around until the matrix it looks nice, and you have a householder matrix, and then you have the original matrix. And then the householder matrices are just rotation, so they're also determinant one, and just like permutation matrices. So they have the sine theta cosine theta kind of thing, if I remember correctly. But
yep, I believe you are hitting the nail on the head there. I was trying to remember where I had it pulled up. Darn it. Yeah.
Yeah, it's just seems all more linear algebra stuff.
Yep. There you go. I think this had a nice little.
Yeah, the triangulation or triangularization somewhere. Yeah.
Of course, you never can find the thing you're looking for when you're looking.
Yeah, they're
trying to. There's a really good graphic. I would say there was a really good graphic that went with it, but yeah.
Okay. Yeah, it's some others. Yeah. All of these are like jumbling together in my head. I took these classes a long time ago.
You're ahead of me, man. Yeah, but there you go. So Hoojboom notes that fixing the permutation matrix limits flexibility, proposed using a QR decomposition where the orthogonal matrix is described with householder transforms.
Okay, yeah, probably QR is done with householder. Yeah.
Yeah. I feel like that popped up here. Yeah. So orthogonal matrices parameterized by householder transform. The idea is based on the fact that from linear algebra, any orthogonal matrix can be written as a product of reflections. So to parameterize it, you fix a non-zero vector, an RD, and then, okay.
Yep,
So
that's the definition of the householder. I think it came across it when I was doing 3D graphics, some custom transforms.
All right. So yeah, so lots of really, there's apparently a lot of really interesting areas to work on in this. From based on what he was saying on the lecture, it seems like flows are a bit understudied relative to some of these others, and I guess it stands to reason that maybe there's a lot more gold to be mined here, especially if you know some clever ways to decompose matrices. So so actually jumping back, that's actually a good segue. Jump back to, oh no, where did it go? Which one is it? It's this one. Okay, can you see it? Should see intermission.
Yep.
Cool. All right. So on that note, so just recapping real fast, we just looked at nonlinear element-wise flows. First, the determinant was easy to calculate. Inversion was potentially very expensive, depending on what we chose for our nonlinear transformation. And there was no ability to capture interdimensional correlations, and this severely limited the expressiveness. So basically, it's limited due to this independence assumption. But along each one of those dimensions, it's potentially very highly expressive. Linear flows, we looked at those with various restrictions. The determinant was potentially expensive to calculate, depending on how we chose our restrictions, but inversion was extremely easy, right? And it does have the ability to capture those interdimensional correlations. However, the linearity is what was limiting the expressiveness. So you can kind of see there's kind of like two aspects here, right? So one is linear versus nonlinear transformations, and then the other is basically what kinds of restrictions we put on those matrices. Right? So nonlinear transformations are going to make inversion very tricky, and capturing all relationships between variables in a transformation may make the Jacobian determinant very expensive. So those are the two big ones, right? So if we want, basically independence and linearity are both limiting expressiveness as well. So yeah. So these two things that are essentially the sources of lots of expressiveness are what are making it most expensive. So we want our transformations to be nonlinear, or have the ability to we want to be able to model nonlinear transformations, and we also want to be able to capture the potential relationships between all these variables. But we also want to do this while still being able to invert it pretty easily and cheaply calculate that Jacobian determinant. So can we find a sweet spot and then rely on composition to achieve our desired level of expressiveness? I'll pause right there. Just so see, this is kind of how I was thinking about it. This is just what was kind of shaking out for me for these like overarching themes here. It's almost like two directions that we're working along here. Like, so if our transformation has the ability to be extremely flexible, very nonlinear, that tends to make the inversion aspect very tricky. But if we also want to capture relationships between all the different variables, then that's where the expensive Jacobian comes in. So, all right, let's jump into autoregressive flows. So an autoregressive flow is just a flow where the dependency between variables has an ordered Bayes-net structure. And then this is from Kobyzev. So just a quick little definition. So we'll let H be a bijection parameterized by theta. An autoregressive model then is just this function mapping RD to RD, where the outputs of each entry of Y are conditioned on the previous entries in the input. So we can choose arbitrary functions mapping essentially RT minus 1. So instead of all of that, yeah, I'll just let you guys read that one. So just trying to read that out loud.
This is just like the Bayes-net, right? So xt is dependent on everything x1 to xt minus 1.
Right. So this is just, yeah. So the autoregressive structure just means the output at time t is only dependent on previous inputs, current and previous inputs. And so this gets back to the triangular matrix thing, right? This is a nonlinear generalization of multiplication by a triangular matrix. So those conditioners, by the way, that's the other aspect of the term there. So we've got like the transformations and we've got the conditioners. So these parameters for this, what was I going to say? The conditioners are going to be dependent on only previous inputs. Right? So yeah, so the idea here is we've got this ordered structure, and for any given point, then that conditioner is only going to be dependent on everything prior to that point, and the output at that point is only dependent on the conditioner and the value at that point. Right? So, so yeah, so what was the upshot of the triangular transformations? Well, if we have a triangular transformation, the Jacobian determinant of the transformation is just the product of the diagonal entries. And once again, then we have a very cheap computation. So that's not bad. So this is good, right? So let's jump into masked autoregressive flows. So the idea behind a masked autoregressive flow is essentially what we just saw on the previous slide, right? So this is going to be very expressive. That forward computation going from X to Y can be parallelized. So that would be this one right here. So in the diagram, it's the left figure. So we can just take a given X and we can immediately go forward into calculating our Ys. But if we want to go from Y to X, on the other hand, that is inherently sequential. It's not efficient, right? So like you basically have to start because like Yn is dependent on all these previous X's. Yn is dependent on x1 all the way through xn. Yn minus 1 is dependent on x1 all the way through Yn minus 1. The only one, so we would have to start with y1. Right? So you'd start with y1, map back to x1. And then you could generate y2, because that depends on x1, and then map back to x2. And then y3, because that depends on x1 and x2, and then map back to x3. So this is going to be inherently sequential. So that's going to be very slow. So basically, for masked autoregressive flows, training equals fast, sampling equals slow. So training is fast because we can move forward in parallel. Sampling is slow because we have to do it sequentially. This is where inverse autoregressive flows come in. So the idea here is to condition upon the previous Ys instead of the previous X's. Right? So why would you do this? Well, it's still very highly expressive, but now the inverse computation would be parallelized, right? So we come over here, we can just immediately generate a whole bunch of Ys, and we can immediately map over to the X's. But yeah, the forward computation, X to Y, is going to be inherently sequential, right? Because you have to start at Xn, goes to Yn, then you can generate, xn minus 1 and go to yn minus 1, because that's also going to be dependent on yn. Right? So if you run this whole thing in reverse, right, that's going to be very slow. But once you have your x's, it's very easy to go. Hold on. Did I get that backwards again? Ah, geez. All right, I knew I was going to trip up over myself here. I guess I will pause for a second. Let's see. Yeah, y to x should be parallelizable. So we go to x2. Yes, I believe this is correct. And then consequently, training is slow and sampling is fast. Sorry, but I tripped up a little bit on that one. But anybody, any thoughts on here?
So basically it's saying we can't have both, right? You have to give one place or the other place. So that kind of leads to the next kind of thing. Can we save both states and then have both, right?
Right.
If you can condition, on previous x on the previous x as well as on the previous y, then maybe we can just use them like dynamic programming, right? And just hold on to the variables.
Yeah. And I guess it's kind of this is kind of where we get into the.
Okay.
So let me jump to. I'll just jump into where I was going to pick up, and this is where it kind of like ended. So I was trying to lead into this because coupling flows are kind of a trade-off between the full autoregressive and the non-autoregressive flows, right? So if you think about it, if you partition half your variables, and then you condition the other half on those, well, that's just a two-step autoregressive. It is autoregressive, right? So it's just, you're only taking one step. Now you could also, partition that differently. You could go through like multiple steps, and you can see that in the extreme limit, you would recover the full autoregressive. So I feel like coupling flows, you can kind of think about those as being a halfway point, right?
Okay.
Yep. And so we will address this more next time. So I wanted to touch on the coupling flows, multi-scale flows. I was going to jump into nice, real NVP. Recursive coupling flows I thought was really nifty. And then we were going to hit the invertible one-by-one convolutions with GLOW, Flow++, Fjord, and then dequantization. Dequantization I don't think is too bad. That one was just basically just adding in a little bit of noise to make your discrete look more continuous, right? But yeah, I just wanted to delve a little bit into some of these architectures because now you have all the building blocks, right? So everything we touched on today, that should make a little bit more sense out of, why did we go with coupling flows? What was this whole thing about that triangular matrix? Where are the trade-offs coming from with expressiveness, right? So, yeah, so those are, I guess we've pretty much hit both ends of the spectrum then. And so this should be a nice lead into nice and real NVP. So with that, does anybody have any thoughts or? All good?
Yep.
Well, cool. All righty. Yeah, so next time I'm going to try and go through some of these architectures and I said, maybe now that we have this background on, I guess, the different aspects that are important when it comes to making this training efficient and expressive, then it'll make a little bit more sense as to why different people have chosen different approaches. I mean, for example, let's throw one in there, like these GLOW, like what made GLOW so special? Right? Well, those invertible 1-by-1 convolutions were generalizations of permutations, right? So back to being able to get sufficient mixing in there. I believe Glow basically just built on real MVP a little bit, but by adding those invertible 1-by-1 convolutions in, and we can see just like how vastly improved that was, right? It's like, well, why would you add an invertible 1-by, like, I remember seeing that when we hit Glow for the first time. I was like, why? What's the point of the 1-by-1 convolution? Well, it's the permutations. Back to one of those earlier slides where we talked about the limitation of the triangular matrix or the triangular transform. You bring the permutation in alongside of it, and then you can essentially get better mixing. You can condition on, you can change that conditioning structure, and Glow is a case in point. So this is a sort of a generalization of what we just saw with the permutations plus triangular transformations in the linear case. Right? And then if you look at recursive coupling flows, this is going to combine a little bit of the stuff we saw with autoregressive with what we're going to see with the coupling. And then real MVP and NICE take advantage of these coupling flows and these multi-scale flows. Which are sort of leveraging some of the same tricks that we saw earlier. Yeah. All right, that's about what I've got for today, unless we want to jump into some other slides or have further discussion.
So I just had one sort of point of discussion to just to think about, because I think all of the flows matrices can be squished into one, and you only have to calculate one determinant, and you could just have one matrix that converts your input to the distribution. So would it be feasible just to have one layer, one matrix, and then just have it calculate the full determinant of it, if it's a small enough image, maybe 20 by 20 image or something like that. So then you have 400, and then the determinant is just I mean it's still 16 million or what, 1.6 million or 160,000, something like that, but it's still small enough, right? Mm-hmm. So if the space is small enough, could you just not worry about it and just say, well, just going to have one matrix that just does it? Or do you really need a sequence of them to be more expressive? Or can you just say, well, all of them will get squished into one anyway, and if it's small enough, maybe that's something we do in the homework, but I was curious about that. So
yeah, I mean, if your transformation is expressive enough, right, you could probably do that, just as long as you satisfy all the basic building blocks. Yeah, you'd have to figure out a way. So as opposed to like that linear case, right? If we go back to, you can kind of imagine, instead of having just these coefficients in this matrix, right? There's generally speaking going to be functions.
Yep.
And in the case you're talking about here, maybe this would be like f theta of x1, conditioned on x2 to xd. So you'd have some general transformation applied to that piece. So you would want to have the ability to condition on all of those other elements, I guess, right?
So what I meant was just that we would just learn f theta of x without anything, and then you have to calculate Jacobian, and you'd have to calculate for everything, but the determinant of the Jacobian, but you just would do it, if it's a 16,000 entries or 160,000 entries for a small one, then it should still be feasible to do. Mm-hmm. So then you could just have one layer of f theta. So you just start with x, go to f theta to z, and then you'd be done. Does that make?
Well, so the question, so the question is, what would f theta be, right? And so no, I totally agree. And I mean, maybe if we made it like a deep neural net or something,
it
would be.
So the theta would be the parameters of your neural net, right? And you just say, okay, it's a function, it's parameterized on it. Just learn one function, then we're done. That just takes x and gives you a z. And
right. But the big sticking point with that is, in general, it's not going to be invertible. So making sure that you still have that invertibility, requirement. Okay. So that's, that would be like, making sure that you've designed a purely, it would need to be like purely monotonic, right? Okay. And for some of those, you might want it to be monotonically increasing. Others might need to be monotonically decreasing. And so then the second you've decided that one transformation is going to be monotonically increasing or another is going to be monotonically decreasing, then you're also constraining it a bit, right? So that invertibility requirement is intrinsically going to be constraining.
Okay, but I mean, if it's CDF, then yeah, I know some of this. Somewhere we're talking about density, and somewhere we're talking about CDF. So, but with like the universality principle, I don't know if this comes in, that you could have one matrix that can, one transformation that can do it. But yeah, that probably, I probably need to think about it more, because yeah, that just means that you're relying on the theta of your
yeah, I think it's, once again, it's going to be back to kind of like that discussion about memory resources versus time resources versus, like, it's all trade-offs, right? You got to, the tricky part is figuring out how to engineer it for your problem to maximize what you want to maximize. And so it may be the case that in some cases where that single, the quote unquote single transformation step is actually vastly more expensive than having a whole sequence of simple ones, that it may be better to go with the sequence, but vice versa. It might be, I don't know, given the constraints of the problem, it might be cheaper, or it might be a wiser choice to do that single step, very expensive transformation. And I don't know, maybe if we're thinking about back to like the inverse autoregressive flow versus autoregressive flow thing, right? If you're trying to deploy something, in production, maybe you need to be able to very quickly generate samples, or you need to very quickly be able to ping it and get an answer. But the training time, could be where you sink most of your, resources. Yeah, I guess it probably depends on what problem you're trying to solve, right?
Yep. Okay. I think this kind of all this linear algebra. There was this field before deep learning. I forgot what it was called, but what you do is you'd start with a linear separator, like a straight line that separates two of them, and then you'd make kernel functions that change the line into like different ways. I forgot what it was called. It was like really big before deep learning.
I'm thinking about like linear discriminant analysis comes to mind, but I'm not.
No,
I'm not sure if that's what you're talking. I don't think you're talking about that.
Oh yeah, yeah, but it was called kernel functions, and you had all these different
support. You're talking about support vector.
Yeah, support vector machines. So you start with a straight line, and then you have all these kernel functions, and you could discriminate between two sets by creating very, very complex kernel functions, right?
Oh yeah, and so on that note, okay, I'm gonna do a shameless plug here for one of my colleagues. Okay. So one of my colleagues. So what's the problem with support vector machines, right? As you said, like who is it? Dude's name begins with a V. Vapnik. Right?
Vapnik, yeah, he was the
Vapnik. Yeah,
he was the author. Yeah, big superstar on that one. Yeah.
Yep. And proved all these wonderful things about it. Made all the statisticians happy. Made all the pretty much everyone in the statistical learning community thought these were the bomb, right? But what was the problem? The problem was choosing the kernel. Was learning the kernel. Like, how do you know what kernel to use? It was just a hyperparameter optimization mess, right? So it was like it's super nice as long as you have a good kernel. So that's the question. How do you choose the kernel? Almost gets back to what you're saying, like we're talking about here. How do you choose that transformation? This is super. All these properties are really nice, but you always got to pay the piper somewhere. And one of my colleagues actually was the first person in our program to get his PhD, Lin Lei. He published some stuff on, he came up with a method he called deep embedding kernel. So basically using neural networks to learn the optimal kernel. And then you get all the nice guarantees that come with a support vector machine, but then you get you learn the kernel as a part of the process. So if anybody's interested in that, I can try and dig up his paper and drop that. But it is really nice, right? Because support vector machines were awesome and they are extremely powerful, but the rate limiting factor is that kernel. And what he managed to do is actually show that you can learn that kernel. You can learn the optimal kernel using neural nets. So yeah.
I think here also you can transform anything distribution into any complicated distribution of your data, provided you have a really nice function in the middle that you have to learn. But it's like computationally very hard. So it feels like a similar kind of problem, right? So that's like you have a simple thing here, and then you're transforming it to a complex thing that solves your problem. Support vector machines did it. But yeah, it was before deep learning, and I sort of like remember people talking about it, but I wasn't. That was before I looked into any of it.
Yeah, but before my time as well.
Yeah,
agree. Cool. But yeah, I'm gonna drop that paper in the chat because I thought that was it was a nifty, innovative kind of thing. Like the kind of stuff where you look at one thing and go, man, this is really strong here and it's really weak here. This is really strong here. This is really weak here. Can we combine these things to make something that has all the strengths with none of the weaknesses?
So it's essentially you learn the kernel and then you fine tune it with SVM, right? Or you fine tune the parameters, the mapping parameters on the kernel.
I'm going to say, sadly, I don't know. I was advised to read his dissertation. I've not done that yet. My advisor was also his advisor, so I do need to actually read his paper.
Well, I mean, if you, I would be very interested. This is very, very, I think it's a very cool idea.
Cool. All right, I'll drop that in the chat.
Okay,
and
great.
yeah, and also I'm going to drop that YouTube video that is going to put my all of my talks so far to shame, and especially the one next week. So I encourage you to watch it, but maybe wait until I present next week so I don't look bad. But yeah, I'm going to put those two onto the feed. Cool. Thanks, guys.
Thanks a lot, Jonathan. Appreciate it, and we like to take homework or collab. Fine, and we should be done. Again, Jonathan, over to next week on some of the papers.
Okay. Well, thank you.
Thanks, Jonathan.